Hi everyone, this is Project Group 24, and our project is on a machine learning mesh-aware upscaling process between a low poly render to a target high-res render without the additional computational costs of the high-res render. So the first step we have to see is how we did the low-res, low poly render, why we did that, and the kind of visual techniques that we use to achieve this.
Hi, so basically the technique we use to obtain a low poly render is mesh simplification. Essentially, by taking the high res high poly render and removing uh, a number of vertices, we were able to obtain the low poly render. And if you were to take a look at the code, since removing vertices results in gaps in the model, we calculate new faces and flat normals. And essentially these methods are similar to how 3JS handles mesh simplification. And by doing this, we remove all the gaps in the model.
And that is the first and very crucial step in our rendering pipeline to generate a both computationally less expensive, since we don't have to calculate the lighting on the much more additional vertices. And also we use the low resolution nature to help with that as well. And so the next step of our project is getting this low res, low poly render to the high res, high poly render. And so let's talk about how we did the machine learning upscaling.
So for the upscaling, we use diffusion models. Diffusion models are basically ML models that gradually add noise to the data in a controlled manner. In our in our in our project, our goal was to learn how to reverse this process to start with random noise and reconstruct the original data step by step. Going over the code for our data, The we used a PyTorch-based implementation of a diffusion model designed for tasks like super resolution. The the model that we used had four key components. The first one was the linear noise schedule. The second one was the diffusion process. This function generated the noisy image for the given timestamps. Then we had the sampling process, which is the reverse process I talked about, where the model progressively denoises the image step by step. And the last step was the training step, where we used multiple loss terms to guide the model's learning. If I wanted to summarize all the four steps, so we start with the low resolution input image, we upsample it to the target resolution. We use the model to predict and remove noise over a sequence of steps. And then finally, in the end, we incorporate the fine details like edges, color corrections, etc. And this is how we basically upscale the image.
And to go more into depth on how we went from a low res, low poly render to a high res, high poly render, we have to first talk about how we collected that data. So in our data collection system, we realized that manually going through and collecting screenshots from different angles was not feasible. So instead, we implemented a random rotation system where we're able to randomly rotate both the low res, low poly render and the high res, high poly render in sync. And then we're able to save screenshots of that directly through the web files API to save the screenshots at each random step. Once we have collected that data set, we fed it into our machine learning model in two phases. So as we have both a image to image system as well as the additional mesh aware, that is the mesh data component, we have to load in two separate sets of data. So the first one is the image data set. We load in this set of data by taking in the image files and then using the prefixes that we generated during our automatic screenshot collection process to create image pairs for the low-res image and the high-res image. This is a very standard process, but the fascinating part on our project is more on the mesh aware portion, where beyond just taking in a low res image as an input, we also take in a mesh data as an input. So the mesh loading part loads in the main object file in the scene, and this object files processing is very similar to how the front-end JavaScript does it during the traditional WebGL render pipeline. And beyond just parsing the vertices and the faces, we also compute features of the mesh to better um, help the model understand how that mesh can be used for upscaling. So one of the crucial features we introduced was the curvature. So by calculating the curvature of the model, we can try to get those lines smoother and make those surfaces more of the high poly nature rather than the low poly one that we use to reduce computational costs. We put that into a PyTorch tensor embedding, and then we use that to condition our model during upsampling. And like Rakop said, we use the diffusion process. And for that diffusion process, we specifically use a UNet. This is a standard architecture these days. But to go over quickly the high level of our UNet, so for each of the image blocks, we use a standard res block. So that is the ResNet architecture. You have convolutional layers plus skip connections. And we have 3 layers of down blocks and up blocks each to get the image into an intermediary representation before reducing the channels and upscaling the resolution back up to the result. And initially, we only had our mesh data as a conditioning that is added to each of the up and down blocks for the image. Later on, we realized it worked better if we use the mesh itself as a downsampling process as well. And for that, we introduced 3 simple mesh down blocks. So the model takes in an input embedding for the mesh as well as the input 200, not 200 by 200, but the input noise step. And then we take that noise step, we feed it through the model. It arrives at the intermediary state and then comes back up through the up blocks until we arrive at the output of the UNet. And like Rakov said, in this diffusion process, we have essentially 4 parts. And the more technical implementations of some of these parts is that to initially scale our image from 200 to 200 to 600, 600, we use a basic bicubic upsampling system to interpolate the low res image to a high res image. We use this instead of something like nearest neighbor because through our testing, this worked the best. And one of the main challenges that we face is that there's a lot of color inconsistencies and artifacting that arise when we use just a standard main square error loss for our denoising. The way we fix this is by introducing multiple more standard image processing metrics to use as loss functions. So some of the ones we use are the frequency domain loss, the edge preservation loss, the color consistency loss. This one was especially important to not generate additional color artifacts and make the output image look consistent with the input image. And the texture consistency loss that calculates the consistency in the visuals within patches of the image. And for the total loss, we added our losses together, but we put in weights that are manually decided and changed during our training process to better facilitate the training. And that is an overview of how our upscaling works, but how it actually gets from the web to the upscale Python is that initially we plan to import the machine learning model as said in our proposal to an entirely web-based system. However, we ran into a problem in the sense that this is not just a one-shot image-to-image model. Instead, we need to go through the entire diffusion process, as well as this model using around 9 GB of video memory, which is not feasible to do on a consumer device. So instead of our original idea, we now have a server that provides this information. So we take a low-res screenshot we gathered, we send that to the server, and then the server then gives out each step of the upscaling in frames. So for each upscaler, we send 20-ish frames to the main web app in order to visualize that process. And to demonstrate, we can again look at, for example, this teapot. So you can see this teapot, especially on the outer ridges here, it's very pixelated. If I can zoom in, these pixels are very apparent and it doesn't look like a circle at all if you look at this part too. But with our upscaling, so we settle on 100 steps because that's a good balance between the model taking a very long time as well as generating a relatively decent image. So our upscaling isn't perfect, but if you zoom in, you can see that the edges are much rounder and more consistent with the real high-res rendered image, whereas the original low-res, low-poly model, as you can see, is very pixelated, and there are much more artifacts than in the machine learning-based rendering. And then we can demonstrate a few more files. So for example, the upside-down egghead, as you can see, we rotate this and then we look at the face. So the face is obviously very pixelated here. If we do an ML render of 100 steps, it introduces, as you can see, it smoothes out a lot of the low res, low poly part, especially where the light hits it. And then if you look at the mouse part, you can see in the original, it is very much pixelated, whereas in the high res version, it's much less pixelated and more of a continuous line. So I'll just show that again. And then if you look at the ear, same thing. This is very hard edges, whereas in our machine learning base, you can still see the edges are there, but it's much more smoothed over, but still retaining a detail and precision that's akin to the high-res rendering. Some future improvements that we can make to our process is introduce textures. So the reason that we didn't introduce textures during this project is that we had to start early because the machine learning part took a lot of time to both implement as well as train. In all honesty, the training took more time than implementation because we had to tweak the hyperparameters precisely to get to our relatively decent results. And in the future, we like to base our project on a more fully featured rendering system with textures. And we also like to improve the quality of the upsampling and as well as the quality overall of our structure and the speed that it generates images for a more um, real-time upscale compared to the more traditional rendering processes. Thank you for listening to our presentation. And my name is Tong.
My name is Raghav.
My name is Alex.
And we're group 24.